ready to go in. Yes, we are live, I believe. Hello, everyone. Good morning, good evening, wherever you are, and welcome to the session on software testing number 3. We have 6 presentations for you. Each will have 5 minutes, and after after all of the presentations are finished, we'll have time for questions and for discussions. But first, let's give our presenters the time to present their work. First up is Dong-Jae Kim on the secret life of test smells.
Okay, so hi everyone. My name is Dong-Jae Kim, and I'm a PhD student at the Concordia University in Canada. And today I'm presenting my research work called The Secret Life of Test Smells, an empirical study on test smell evolution and maintenance. I hope you guys enjoy this short talk. So softwares are becoming increasingly complex over time. With increasing user demands, tremendous collaborative effort takes place to deliver features on time. Therefore, software testing plays an important role in validating software quality. Its role is to detect bugs early on in the development to reduce later costs to fix defects, and eventually, it also keeps the customer satisfied. Unfortunately, even tests are prone to design issues, and recently, these design issues have been coined the term test smells. And the presence of test smells negatively impact code comprehension and maintainability. Since the introduction of test smells, many test smells have been proposed to improve the test code quality and the test case designs. Unfortunately, many proposed work lacks validation on 2 aspects. So the first is it isn't clear whether test smells are truly harmful. And second, it isn't clear whether developers really truly care about the proposed test smells. Without such knowledge, future studies will continue to propose new test smells and detection tools, and many of the works on test smells will have a minor applicability in the wild, and which may eventually slow down software maintenance efforts in the future. And so we propose 3 research questions to validate the current perception and awareness of test smells in practice. First, we looked at how test smells evolves in the wild. Second, we looked at what is the mechanism for removing test smells. And lastly, what is the relationship between test smells and software quality? And to carry out this research, we use an off-the-shelf test smell detection tool proposed by Anthony Peruma. And we use this test smell detection tool because it detects a comprehensive list of test smells with a high average F-score. And a lot of the test smells overlaps with many prior works that are extensively studied. Therefore, the 2 criteria makes the tool a good candidate to validate the current perception of test smells in practice. And we use the tool to study on 12 open source Java projects. Our first research question studies how test smells evolves over time. In summary, to study the evolution, we run the detection tool on 18 test smells every 6 months between 2016 and 2019. Then we plot the test smell evolutions for each of the study systems. And we also calculate the test smell density by normalizing the number of test smells with its total lines of code. And we call that the test smell density. We then plot the second figure for the test smell density evolution. In our work, we compare the 2 evolutions between the 2 plots. In summary, we find that test smell density generally remains stable over time, even though the total number of test smells in the system increases. Our second research question studies what is the reasons and mechanisms for removing test smells. To answer this question, we categorize our findings into groups. The first category is called the test smell aware refactoring. It is the test smells that are deliberately fixed by the developers. And second category is called the test smell unaware refactoring, and it is the test smells that are accidentally removed as a byproduct of other maintenance activities. In summary, we find that there's an inconsistent strategy for test smell removal in practice. So while the test smell may get removed deliberately, but sometimes they may also persist and even become magnified through refactoring activities. And finally, our third research question studies what is the relationship between test smells and software quality. To answer this question, we used a past 6 months data to find a relationship with the defect in the future 6 months. And for our predictors, we use 3 main class of metrics. The first type is the traditional product and process metrics. And the second type is the coupling metrics. And the third type is the test smell product and process metrics, which is the metrics of our interest. And for response variables, we have labeled post-release effect at the test file level. For a model, we use a logistic regression model to study the relationship between the test smell and the post-release effect. And we use a simpler model because our goal is not to predict the defects, but we wanted to understand the effect of test smell metrics, the test effect of adding test smell metrics on the post-release effects using a more interpretable model. In summary, we find that the test smell improves 8.25% increase in AUC, but most of the test smell metrics have a low probability of post-release effects.
Thank you very much.
Yeah.
I think we have time for the next speaker now. This is Marcel Böhmer, who is going to present to us statistical reasoning about programs.
Can you all see my screen?
Yes.
Okay, wonderful. So this is Marcel Böhmer. I'm a faculty member at the Max Planck Institute for Security and Privacy, and I'm here to talk about my paper on statistical reasoning about programs, which is a vision paper in a near track. So, how do we do formal reasoning now? Formal reasoning is the approach that we take to reason about programs currently. So to formally reason about a program means to interpret its instructions according to a given semantic rules. So any programming language has syntactic rules, which defines the structure of the language, and semantic rules, which defines exactly what the machine should do for each instruction of a program. So to formally reasoning means to interpret those instructions to the machine according to these semantic rules. And now it derives, using these interpretation, it derives a model of computation. And this model of computation describes the relationship between the inputs and outputs of the program. And then it computes the property of interest, like does there exist a bug, or is there an information flow from this statement to that other statement within this model of computation. So what happens is essentially the static analysis takes this program source code and generates this idea of the program behavior, of the program's behavior. And so this idea is called the model of computation. On the other hand, you have a compiler and a linker which takes the program source code and actually produces the binary, and that binary is being executed and then exhibits this runtime behavior. The problem of formal reasoning is that there might be a gap between the idea of what the program does and what the program actually does. For instance, you want a static analysis to scale, so you trade scalability for soundness, or you trade scalability for completeness. And so the difference between this model of computation and the actual runtime behavior of the program might be very, very high. Secondly, there are problems with understandability, but the consequence is always that the model of computation may be incomplete or incorrect. Of course, formal reasoning has achieved a lot of. We have a lot of tools based on this idea of computing an abstraction, and we have achieved. There's a lot of other formal achievements in using formal verification, for instance, for an entire operating system kernel. But the problem is that we don't really get any guarantees anymore. As soon as you left this idea of trading soundness or completeness for scalability, we started to report bugs that don't exist, or we do not report bugs that do. But we cannot really quantify the degree to which our analyses are incorrect. So this is the starting point for this idea. So what we need is scalable sampling-based in vivo program analysis. We can do this in an observational setting or in an experimental setting. We essentially observe the execution of the program, or we modify the execution of the program and then reason about this modification. So statistical reasoning then means to extrapolate from the sample of these executions to the entire population of all executions. And you can do this with quantifiable accuracy. That means you don't have any false positives, but you can quantify, you can bound the false negatives. And that for programs of arbitrary size, any kind of system. And you can always trade better efficiency for a lower sampling rate. But in this trade-off, you can always remain this keep these guarantees. And so in my paper, I lay out a roadmap for this idea of statistical reasoning. and also point to many opportunities, but also many statistical challenges that need to be tackled. And what I think is that statistical reasoning about programs kind of provides us with a different lens through which we can look at the program analysis problem. We can measure properties of systems of arbitrary size and measure those the degree of uncertainty. And this is essentially what statistical analysis is being built for. Thanks.
Thank you very much. And you helped us catch up on time a little bit even. Much appreciated. Next up, we have SymTuner, presented by Soo-Young Cha on maximizing the power of symbolic execution. Please go ahead.
Okay. Hello, everyone. I'm Soo-Young Cha from the Sungkyunkwan University. So in this talk, I'm going to talk about a new technique called SymTuner. So the goal of SymTuner is to automatically tune the many external parameters of symbolic execution via online learning. So this work is co-op with Myung-ho, Seok-hyun, and Hak-ju from Korea University. Okay, let's start with the motivation of this work. So as you know, symbolic execution is one of the powerful white box software testing methods. So in general, this technique takes a source code as an input, and it aims to automatically generate the test cases that are likely to trigger the program crashes or increase code coverage effectively. And because of its well-known effectiveness, many symbolic execution tools such as CLI and Sage are actively both in academia and industry. However, when we try to use these practical symbolic execution tool, there exists an additional but essential process. Yes, the process is that we have to determine the diverse parameter values of symbolic executions. So in this work, we define the parameters of symbolic execution as any factor that critically affect the effectiveness of symbolic executions. And in general, tuning these parameters is highly important to achieve high code coverage or find subtle bugs. But the problem is that there exist numerous parameters of symbolic executions. So this figure shows the typical parameter setting of the symbolic execution tool CLI. So as you can see, there exists very specific specialized for symbolic execution parameters, such as max memory or search or symbolic argument. So naturally, the challenge is that manually tuning such parameter is really difficult, not only for end user, but also for domain expert. So it will be really challenging to determine appropriate value for all of these question mark consist of Boolean and integer and string types. So let's see how, before introducing our work, let's see how the prior work to handle this parameter setting. So first, they usually use the default value or the hand-tuned value provided by the original author of symbolic execution tool. Or otherwise, some specific parameter value are manually adjusted for each target programs. For example, the parameter symargs are manually adjusted for each target program differently. So my motivation is that manually tuning this parameter is really time-consuming and labor-intensive. So this is my motivation. So in this work, I'm trying to automatically tuning such parameters for each target program. So our technique called SymTuner takes a symbolic executor and target program and the parameter spaces that we want to tune. So for example, the parameter spaces can have 4 candidate parameters, and each parameter has consists of a set of possible values. So after taking this as an input, and SymTuner iteratively sample this parameter value from the predefined spaces and execute this sampled value with for perform symbolic executions. And so the goal of SymTuner is to learn which parameter values to sample from these spaces. And to achieve this, we present a custom learning algorithm for effectively learning the sampling probability of each parameter space during the symbolic executions. And as a result, over the 12 open source C programs, SymTuner consistently achieved the 31 and 56 more branches on average compared to the 2 baselines without the parameter tunings. And we also found 11 different bugs in the latest version of C programs. So we found segmentation fault or abnormal termination and so on. Okay, let's sum up this talk. So to best our knowledge, SimTuner first tries to automatically tune the parameters of symbolic execution via online learning, and we make our tool publicly available. And lastly, we hope that SimTuner will help end user to maximally benefit from powerful but difficult to use symbolic execution tools. Okay, this is the end of my talk. Thank you for listening.
Thank you very much, Soo-Young. Next up, we have Kunpeng Zhang on path transitions and how much more they tell us about how to optimize our fuzzing.
Hi, my name is Zhang Kunpeng. I'm a postgraduate student in Tsinghua University, and I'm going to present path transition theorem, optimizing fuzzing schedules via one-time program states. Fuzzing is a widely used tool to expose security issues in software. Existing solutions to improve the efficiency are twofold. The first category intends to reduce search space of inputs, and another category is to optimize path schedules. For the first category, the existing solution to reduce the input space is to infer the relationships between input bytes and path constraints, which improve the efficiency of resolving path constraints. However, a real-world program could be far more complicated, as the byte constraint relation could exist between multi-bytes and multi-different constraints, or even nested. As the inference relies on the changes of execution states, the changes can be explicitly or implicitly influenced by the mutation of certain bytes. Thus, when the inference process intends to infer the related bytes for the inner condition in a nested condition, the result may erroneously include the bytes related to the outer condition. As a result, when fuzzing intends to resolve the inner condition, fuzzing may mutate the related bytes of outer condition, which will alter the branches of outer condition. To avoid this problem, we observe that the difference between two execution paths of a path transition imply properties of programs. Specifically, the paths that examine the error handling code are usually much shorter than the paths that examine functional code. Based on the observation, if the mutation of certain bytes results in a significantly shorter path, these bytes are likely related to a validation check. Then we can identify the bytes related to validation checks and protect those bytes from being frequently mutated, making most general weighted inputs examine the functionalities of programs instead of being rejected by the validation checks. In order to determine such a relationship, Trust computes a fitness for each byte by mutating it and observing the difference in a path transition, measuring how likely a byte is related to a validation check. Based on the fitness score, Trust then assigns lower mutation possibility to the validation-related bytes, protecting them from being mutated. The difference in a path transition also optimizes the seed prioritization. If a path transition discovers a path that includes many new edges, it's likely to explore an undiscovered code region. More new edges covered in a path may lead us to more undiscovered descendants, as it may have touched more new code regions, so that we should focus more on such seeds that discover more new edges until they have been tested. In order to prioritize seeds, Trust ranks each seed based on the number of new discovered edges when a seed is first returned. To evaluate our Trust, we implement Trust with seed fuzzers and compare the performance with the corresponding vanilla fuzzers. First, we want to figure out how effective is byte analysis to guide more generated inputs flow into functional code. As shown in the figure, under the same conditions, Trust-equipped fuzzer can generate more valid inputs than the vanilla fuzzers. Second, we run two versions of fuzzers on A programs for 24 hours and compare the average performance with respect to code edge coverage. Trust-equipped fuzzers discover more new edges than the vanilla fuzzers. Third, we compare two versions of fuzzers in terms of the number of real-world bugs. In total, vanilla fuzzer and Trust-equipped fuzzer find 10 and 13 bugs respectively. Finally, we summarize our work. First, we propose a lightweight framework Trust to improve the performance of SageGFs. Second, we evaluate trust with respect to value input generation. Third, we implement trust with sys fuzzers and compare the performance with vanilla fuzzers. That's all. Thank you.
Thank you very much. That was very efficient. And next up, we have Du Zhengji presenting Wind Ranger, directed gray box fuzzing driven by deviation basic blocks. Take it away.
Hello everyone. Next I will introduce our work, Wind Ranger, a directed gray box fuzzer driven by deviation-based blocks. Gray box fuzzing is an important software testing technique for finding vulnerabilities. However, general gray box fuzzing aims to max coverage of the whole program, and it makes the directness to reach predefined target locations. Directed gray box fuzzing aims to steer the fuzzer towards predefined target sites in the program and is useful in some security scenarios, such as patch testing and crash reproduction. Existing distance calculation may have two pitfalls. First, the seed distance calculated with all the base blocks on the execution trees. It treats every base block equally. However, some base blocks are the key of driving the execution towards the target size, and may be more important. Second, the seed distance calculation is only based on control flow information, which counts the edge number. However, different edge has different difficulty to pass, which is state flow information. Next, we use an example to discuss the pitfalls. The left is a code select, and the right is a corresponding execution trees of three different seeds, A, B, and C. The circles represent the base blocks. The number represents the base block ID and its distance. Read load is the target base blocks. For seed A and B, if we calculate the distance with all the base blocks, the seed executes. The distance of A is bigger than the distance of B, so we should for B than A. However, from the graph, we can see that seed A executes node 21, which is closer to target 22. Intuitively, we should prefer A than B. A comparison between seed A and B shows that the seed distance calculated with all the base blocks can be based. For seed C, it has the smallest distance. However, the condition on line 15 is very hard to pass to target 16. It shows that only use the control flow information to calculate the distance is not enough. Data flow information should also be considered. And there are certain base blocks that deviate the control flow from target sites. We call them deviation-based blocks. DBB in short. If we calculate the distance by average only in the DBs, and if we can further adjust the distance of seed C according to the data flow information of DBB at 15, we can eventually improve for seed A. Wind Ranger leverages deviation-based blocks to guide DGF. It mainly contains two stages, identify DBBs and fuzzing based on DBBs. To identify DBBs, first we use static analysis to find the potential DBBs for the whole program. Specifically for a base block, if it has unreachable successors and reachable successors, this base block is a potential DBB. In dynamic fuzzing, if a seed executes unreachable successors, the base block is DBB, or it is not DBB for a seed. In fuzzing, Wind Ranger leverages DBBs in 4 components. For seed distance calculation, Wind Ranger uses only DBBs at the number of input bytes and influence DBBs as a degree of difficulty to calculate the distance. For data flow sensitive mutation, Wind Ranger identifies the inputs bytes which influence the DBBs. These input bytes will get more chance to be mutated. For seed prioritization, Wind Ranger prioritizes which executes new DBBs. These seeds will get more chance to be selected to mutate. To avoid getting stuck in local optimal, Wind Ranger dynamically switch between the exploration and exploitation stage according to the execution time of DBBs. We evaluate Wind Ranger with these datasets and tools. In target site reaching capability experiment, we evaluate how much time different fuzzers cost to reach predefined target sites. In bug reproducing capability experiment, we evaluate how much time different files cost to trigger the known crashes in Google File Test. In impact of different components experiment, we disabled each component individually to investigate the impact of different components. And MidRanger has also found unknown bugs in practice. Thanks.
Thank you very much. Then, as our final but certainly not least talk, we have Wenqiang Li presenting to us microAFL non-intrusive feedback-driven fuzzing for microcontroller firmware.
Okay. Could you see my slides?
Yes.
Oh, okay.
Very good.
Okay, I'm Wenqiang Li from the Institute of Information Engineering, Chinese Academy of Science. Today, I will share you with my work, the microAFL non-intrusive feedback-driven fuzzing for microcontroller firmware. Today, the IoT device is becoming ubiquitous in our daily life, especially the MCU-based embedded device. Also, they introduce many vulnerabilities. And if given a firmware sample, how can we find bugs in it? Some existing tools, for example, AFL, A-SAN, and CS2E, they cannot be used to test the MCU firmwares due to the lack of a memory management unit. And recently, there are two approaches proposed to test MCU firmwares. The first, the emulation-based rehosting. It tries to run the firmware in the emulator and model the peripherals, but it cannot handle complex peripherals, for example, USB, and they incur high false positive and negative due to the low emulation fidelity. Another, the hardware in the loop approach, they also try to run the firmware in the emulator, but forward the interaction with peripherals to the real hardware. However, they require frequent and expensive switching and syncing. So in summarize of the existing challenges, we propose microAFL. It's a new fuzzing solution specifically designed for ARM-based MCU devices that address the aforementioned issues. We have three design tools. For the first one, we try to support fuzzing complex firmware, especially the peripheral drivers. We decouple the execution and analysis. We provide one online trace collector and one offline trace analyzer from the PC. And for the second goal, we try to support gray box fuzzing. Also, a naive idea is that we could instrumentation. However, it will incur high overhead, and for binary, the binary writing strip is still challenging. So we choose to use a hardware feature called ETM to collect the instruction trees. This hardware will directly generate encoded packets about branch information at the runtime. With the collected instruction trees, we could decode the raw ETM data and alien it with a assembled firmware binary as the ETM protocol described. However, this will incur high overhead. So we choose another runtime information analysis. We propose the linear code sequence and jump basic block. It's an instruction sequence that starts from the last taken branch target and end with a subsequent branch instruction, which is actually taken while the firmware running. It can be represented by a starting address and a subsequent branch of information, which are directly available in ETM. We do not need to analyze all the instruction trees, for example, interrupt, booting squeeze, and so on. So we provide two online trace filters with another hardware feature, DWT, and we also provide an offline trace filter by analyzing the exception information in the ETM protocol. To evaluate our work, we answered these questions. The first one, how is the Lucidity basic block approach improve performance compared to the approach that fully recover the instruction flow? So we implement the fully disassembled and decoding one, and it compared to the microAFL result is shown here. For the research question 2, do online filters help to improve the performance? We also disabled the filters for microAFL and compare the results of them. For research question 3, how much overhead does MicroAFL introduce to a single round of fuzzing? We tested each sub process of the single round, and we can see the more complex the formula is, it will consume more time to run and more time to analysis. For research question 4, what is the overall performance of MicroAFL? We test some real-world formulas and get the result here. And how is compared with the existing work? We compared MicroAFL with emulation-based approach and the hardware-in-the-loop-based approach. For research question 5, how effective is MicroAFL in locating bugs? We test some real-world samples and we found 13 zero-day bugs in the USB stack. So in summary, we propose MicroAFL, the first practical tool to fuzz complex driver code for MCU, and we found 13 zero-day bugs and get ALIN's 8 CVEs. Our work is open sourced here. Thanks for listening.
Thank you very much. So let's give a round of thanks, perhaps using the emojis or however you choose to our 6 excellent speakers. This was all very great work. I'm very impressed by both the breadth and the depth of what's been going on here and the very effective compression of such considerable amounts of work into just 5 minutes by everyone. Now, before we start with discussions, I would suggest that we go through the papers very quickly and ask if anyone has any questions about questions for clarification on the individual pieces of work. So would anyone like to get any clarifications on Dongjae Kim and from Dongjae Kim and this work on the secret life of test smells and the empirical study on test smells? Yeah, so feel free to speak up or write a text question if you have any. Otherwise, just feel free to write them down or speak up. I will go over the names of the talks. If that's a bit out of sync, I don't think that's a problem. Next up, we had statistical reasoning about programs by Marcel Böhmer and how to integrate that into better understanding how our programs behave and where there might be bugs or optimization opportunities. Any questions on that space? Next, we had SimTuner, maximizing the power of symbolic execution by adaptively tuning external parameters by Soo-Young Cha, and the application on CLI and the parameter spaces there. Then we had Kunpeng Zhang and path transitions. Tell more, optimizing fuzzing schedules via runtime program states, using program state information to more effectively perform fuzzing. Then number 5 was Windranger by Du Zhengji, directed gray box fuzzing based on the idea of deviation basic blocks and how to use static analysis to find those and drive the fuzzing process. And finally, now we had MicroAFL, non-intrusive feedback-driven fuzzing for microcontroller firmware. So I don't see any requests for clarification questions. So then maybe let's just open it up to any sorts of questions. Any high-level, low-level questions that you would like to bring for the authors?
So I have a question for the Kunpeng Zhang. So it is a very simple question. So have you tried to use the AFL++ for instead of AFL for evaluations? Because
I didn't integrate our method into AFL++, but I think it will be finished in the future work.
Okay, thank you. Because as I know, AFL++ has much more powerful than AFL, so I just wondering about that.
Oh, I know that.
Okay, thank you.
Thank you. Any other questions?
I have one question for Song-Yang. At the evaluation force, what is the difference between the hand one and the random tuner? I think the hand is chosen by the human and randomly. So I think both is random. So I don't know what is the difference between these two.
Your question is what is the difference between the hand-tuned and
Random.
a land tuner?
Yeah, the hand one and the random tuner. I see you compare them in your evaluation.
Yes, hand tuner is the fixed. They use the fixed parameter values. So during the symbolic execution, they do not change the parameter values. For land tuner, while performing symbolic execution, they randomly change the parameter values during symbolic execution online.
Okay, thank you.
Thank you.
Thank you. Any further questions? Well, if nobody else has any questions, I have a couple. Let's start with Doongjae. I had a question about your work on test smells where you noted a positive correlation between some test smells and later defects. So that was for the third part of your work. And one thing that I was wondering about there was you noticed that there were some very particular test smells that seemed to correlate with these defects. Would you say that that correlation is because those smells just in general reduce the quality of the tests, or that the smells are kinds of code that happen to occur when people test certain kinds of APIs, and that those kinds of APIs or kinds of code are just intrinsically very error prone, so that it's not the test itself that is bad, but rather that the type of code that you need this for happens to be very error prone?
I agree with the latter description. I think some of the test smell, definitely it's related to the error handling, right? And then the other ones are more related, like for example, there's a test smell called exception handling practice, and definitely that's more prone to like defects. And then also some other test smells like I think conditional conditional logic also kind of like had a higher defect prone. But then yeah, so I definitely agree with your latter. And those things are the test smells that are consistently having higher like probability of defects. But the other ones are really like very system dependent. It's not very transferable across different systems.
Mm-hmm. Yeah, that makes sense. Thank you. Do you think that there's any lessons that you can see already that could be taken away from perhaps making certain kinds of code easier to test that current languages or test frameworks perhaps don't give us?
Making tests more testable?
Making those particular test cases that tend to exhibit these kinds of smells more testable. I don't know if you have an answer. That's a very high level question.
I'm not sure what. Okay, well, I don't know if it would make it testable, but in this work we were more interested in whether like some of the test smells are like actually worth studying, because there's like so many test smells that are like being released literally every year. And so we wanted to kind of understand like what really matters for the developers. And in the paper, we actually noticed some explanations for why developers fix those test smells more than the others. So I guess our summary is that maybe for those particular test smells that are fixed more, maybe you should kind of like understand why developer fixed them, and then maybe you can also apply a similar strategy for yours, because we also provide some mechanisms to fix them.
Yes, excellent.
Yeah.
Thank you. And I think it was quite insightful from that perspective. So then let's see, the next person who hadn't received any questions yet would be Marcel with statistical reasoning about programs. And I think that the first question I would have there would be, what kinds of program properties do you see as the properties that you would particularly want to analyze with this? Do you see this as something very broad that captures everything that static analysis gives us these days, or more towards dynamic analysis, more towards optimization, more towards bug finding?
So I'm a bug finding person, so I know that there are efforts to scale bug finding. For instance, if you have an Android phone and you run Android R, or if you run a Chrome browser, or if you run a Linux kernel, there are very efficient bug finding mechanisms that are essentially zero overhead bug finding indicators. Zero overhead because they are sampling executions and they're only enabled for a fraction of executions. And across a large base of users, like all Android phone users that have a specific Android version and then upwards, or all people that use a Chrome browser. And so while the signal on one machine is very small, the signal across a lot of machines is large enough to reason about bug finding, for instance. But yeah, bug finding currently, how this is done is essentially you have a user at the interface and you have bug finding at the end. But static analysis is much more fine-grained than this. It reasons about each instruction in the program. I guess what we can do in the future is firstly combine these two things, reason statistically and statistically and using formal reasoning. But we can also make statistical reasoning more fine-grained in the sense that you kind of inject probes into your software at different points in your software. You don't even need to inject it. You just need to observe the execution of the machine, like on a hypervisor or in the operating system, and then at different points in the execution. Okay, here's an example. We published a paper a few years back where we looked at information flow. Information flow is you don't want to leak any sensitive information. You have a sensitive source and a public sink. And so static analysis would then go and look at dependencies. And the problem is obfuscation. A problem is if the information flows through the internet somewhere, you lose track. So what you do is you havoc. You say at these points where it goes into some third-party library or towards the internet, you just havoc. Anything can happen. What we do is we modify the execution at a sensitive source and split that into a shadow execution. And in this shadow execution, the value of the public of the sensitive source is changed. So then we look at these two executions, in the shadow execution and the real execution, and add a public sink. At any public sink, we can just look at whether there's a difference between the values received in a public sink. If there is, then obviously because of our experiment, we can see an information flow. All obfuscation problems are solved, and we don't need to do any kind of static analysis and look at the source code for arbitrary. You can do this analysis for systems of arbitrary scale. So this is the kind of analysis that I kind of envision. But beyond that, I also envision that you don't only say that there is an information flow, but you can also quantify that there is no information flow, at least statistically.
Mm-hmm. Thank you very much for the explanation. So let's now say that let's say I'm a developer. I'm really excited by your methodology, and I have an app that I don't know a couple of thousand people have downloaded. How would I now use this practically as someone who does not control the platform that the program runs on? Do you think that's practical, or is this going to be something?
So what you can do is if you can. So there are compiler passes. So most of fuzzing is being done using compiler passes. So what we need in fuzzing is inject coverage feedback. And people have explored different kinds of coverage feedback. We have Cheng Jie, who explores how to direct the fuzzer using certain kind of coverage feedback, and he optimized that coverage feedback. So it doesn't matter which program you do. You just push a button, and this coverage feedback is injected into any program. And so if you have several Android apps and you're developing those, you just need to develop this compiler pass for Android and push a button and compile it with this, including this analysis. That would be one opportunity if you don't control the platform.
Okay. So basically, when someone installs the app or downloads the app, they'll get appropriate instrumentation that's then selected, something like that. So
yeah, the phone
staged
spec,
approach. Okay, I could see that. I would have more questions on your direction, but let's first see if we have some more questions from the audience, perhaps, or from someone else. Then otherwise, maybe let's give Suyong a question, because no, hang on, you already had a question. Who did not have a question, however, was Du on Windranger. And here I had a question for you on the use of interprocedural CFGs in your work. And you in your work you're using interprocedural CFGs, and you're comparing yourself against AFL-Go, where the author, who also happens to be here, noted that using intraprocedural CFGs was quite valuable for performance. So I'm curious what your thoughts are on that. Did you find that it was much cheaper nowadays to get intraprocedural CFGs for those programs you were looking at, or was the benefit overall justified to switching to interprocedural CFGs?
Thank you. You see, you ask if we want to increase performance.
Yes.
Yeah, actually, we use some what we use is some NetWare dictionaries to in dynamic. So actually, there has don't have many performance, don't cost many performance, and
So what would you say is the overhead that you take for getting the interprocedural CFG for your programs? Is it less than a couple of hundred milliseconds or something like that?
Sorry, I don't actually understand your question.
Sorry, my question is the overhead for getting the interprocedural control flow graph time-wise. Did you find that to be a very low overhead, or just something that you were able to get?
Actually, the analysis of control flow graph is in static stage. So in dynamic stage, there has not very much overhead because a lot of analysis we have done in static stage, and we have got enough information in static stage. So in dynamic stage, we don't do any too much comparison work, like a comparison work.
Okay, thank you. So we have a question from the audience here. Let's maybe take that one, unless someone wants to follow up immediately on this one. And that one is to follow up on the static analysis question. This seems to need an experimental. This needs to need an experiments telemetry framework, and that's going to the question I had about the. I'm an independent app developer. I think, how does that get with communities that do not consent to telemetry? Is there thoughts towards how to ensure things like differential privacy if the data gathered, or other similar guarantees? So that goes to you, Marcel. The question is also in text in the chat if you want to read again. So this is about what kind of telemetry or similar framework does one need in order to make your approach work, and how does one deal with differential privacy, which I think you talked about in the paper.
Thanks, Professor Petru, for this excellent question. And so this is a vision paper, and we point out to exactly those challenges, including privacy. And yes, so what I imagine is you don't need to capture traces like in dynamic analysis, where you need to take the actual execution and send this trace to to the user, or you don't have, like in Mozilla or Chrome, where you have a bug and then you want to send all the entire context of that bug to the like phone home to the company, and then the company at home can debug this. This is not about debugging. This is about distributing the analysis problems across many machines. And and then making so the actual starting point for this problem was that in static analysis we make all these trade-offs, and suddenly we report bugs that do not exist, and we do not report bugs that exist. And so now we are tackling this false positive problem. There's a lot of research on trying to kind of get a handle on this false positive problem, but we don't. What it means is we don't have any guarantees anymore. We don't get any guarantees. So we don't even understand how to quantify this lack of guarantees in static analysis anymore. Statistical analysis, though, exactly helps you to quantify this. So this is the starting point. The problem with privacy is a problem, but you can imagine any other program analysis problem where your personal data is not involved, that you can still reason about. You can even kind of conduct some analysis on the like on the user side or in the cloud that aggregates and kind of makes sure that privacy is upheld. So definitely this is a concern, but this is not the main caveat of this kind of analysis.
Thank you. So follow-up question on, or follow-up point on, this could be a challenge if someone has a particularly esoteric setup. And to give an example of something like that, let me add on something to that question. A colleague of mine is working on, Benoit Boudry at KTH, looking at mutating software to make it more diverse explicitly. So the idea being that by mutating the software without changing the behavior, you might reduce the global attack surface of a program by reducing particular special case bugs, vulnerabilities that only apply to certain alternatives here. And if we now have all these small mutations in our programs, or if we have someone who maybe used a very obscure module for just their particular operating system, how does that now factor in here with the distributed statistical analysis that you have in mind?
Can you
if I'm interpreting this right?
Yeah,
I was rambling a bit there. Sorry. So let's maybe stick closer to the answer. Esoteric setup here being that we have your program that you're trying to analyze. This program depends on, let's say, some dynamically loaded code or some configuration variables. And for 99% of the populace, this is very specific. And here is someone running your program on Amiga OS and has some very obscure settings that don't affect anyone else. How would that work in your setting?
Well, you find a bug where you would not otherwise find a bug, right? In static analysis, you make no assumption about the machine, but here you suddenly find that. So actually, you make assumptions, implicit assumptions in static analysis about a machine. So if you suddenly find a bug in your program because it is running on Amiga OS, then of course it's hopefully a valid bug, and it should be reported and then fixed. For people that actually run, if there are a lot of people running Amiga OS, you want to cater to them as well, right? So you want to have some signal from them as well. Mm-hmm. So exactly this kind of distinction between the model of computation that we reason about in formal reasoning and the actual execution that we then see in production. This gap is essentially what I hope to address with this idea of statistical reasoning.
I think there's one step further that one can go here, and that is that the properties that you would want to capture with statistical reasoning, I would expect would be not necessarily just properties on whatever is specific to the operating system that you're running on, so Amiga OS in this case, but also properties of the layers above that include that specific piece of functionality. And then there would be information from the Amiga OS module that tells the layer above, for instance, well, this value can actually be 0, or these 2 pointers can actually be aliased. So that would give you a more general contract for the layer above that is not really specific for that sublayer, but rather just happens to be instantiated in that situation. So I very much see the appeal of your proposal in that space.
And you can easily think about integration of both, right? Aesthetic analysis
Yes.
and statistical analysis. Aesthetic analysis being over-approximating and essentially giving you the space of all states in your program, even states that don't exist. And statistical analysis kind of being these kind of building a distribution over that space of
Yes.
what can actually happen in the system.
Right. Now we have 5 minutes left. We haven't had any questions for Wenqiang Li yet on micro AFL. Does anyone have any questions in that space? Otherwise, I have just a very high level question. You mentioned that this work that you've proposed is very good for or is designed for a certain set of ARM devices. And I was just wondering, what's the general requirement, would you say, to exploit your insights? If I had a different kind of device, might I still be able to apply it? And what would be the requirements for my hardware? And what might I be able to supplant in software?
Yeah, get it. Actually, it relies on the hardware feature of ARM. So I say this work is for ARM-based devices, the ETM, the WT, and also we believe that other architecture and device also may have their own hardware features. For example, the InterPT. And I'm not familiar with RISC-V, but I'm sure that I believe there may be some other hardware features that could help to collect the instruction trees without any effect on the program execution. So this is a high-level idea, and we implement in the ARM-based devices, but we believe it could be used to other devices. The decouple idea and the hardware feature idea. Yeah, that's all. Thank you.
Thank you very much. That was also my impression, that it's not that hardware specific. So then I think everyone has had at least one question, unless I missed someone. And we have 3 minutes left. Any last questions? Anyone who has some really exciting thought on their mind that they want to share with us?
Okay, so I have a question. So I have a question about Zheng Jidu, Wind Ranger. So I'm not familiar with directed gray box forging, but what kinds of target site did you use for evaluations?
The targets we use it in the experiment for target site ability experiment. We selected target sites. First, we use AFL as a baseline. We run the AFL and collect the information for a program. Collect the information about each location in program. How much time AFL cost to reach this location, and based on this information, and we select the target sites from the information, and actually we use different time cost difficulty level to select target sites.
Okay, thank you. I think it is reasonable. So have you tried to target site as a new patch code or something like that?
Sorry, new what?
So have you tried to use the target site as a new patch code? The goal of your
use a new patch code as the target sites.
Yeah.
We don't use new patch code, and in our last experiment we use assert locations in program as the target sites, and we found a box in reality program.
Okay, thank you.
Yeah, thank you.
Hi, Christoph. You are mutated. We can't hear you. You are mutated.
Thank you very much for catching that. Yes. So thank you very much, everyone. I think we are pretty much out of time. So thanks again very much to all of our excellent speakers, Dongjie Kim, Marcel Böhmer, Zuyong Cha, Kumpeng Zhang, Du Zhengji, and Wenqiang Li. I hope that